This is the video recorded lecture for aircraft pressurization systems. You need to take lots of notes. I recommend if you have any questions that you put an asterisk next to the side of the page and then send me an email or ask me about it next time we're in class. Okay, aircraft pressurization systems. Make sure that you do the Boeing 777 computer-based training program on heating and air conditioning, pressurization. Fill in the blanks in the homework. Make sure you can answer those homework questions for the next test. The purpose of pressurization systems is so that you don't have to use oxygen. If you had to use oxygen, it would add a lot of weight to the airplane, for the oxygen system, for the oxygen. But probably the most big problem is trying to train 100 people how to correctly use oxygen systems. The other thing is if you go above flight level 250 or 25,000 feet, your likelihood of having other high altitude sicknesses in addition to hypoxia, not enough oxygen, even if you are using the correct oxygen system, is dramatically increased, so you don't want to have those. And you're going to have to heat the cabin anyway. At 36,000 feet to 86,000 feet, standard day temperature is minus 56 degrees Celsius, and so it's awfully cold. You're going to have to pump some kind of warm air into the cabin anyway. How do you take care of all of this? What's the function? You do it by keeping the cabin at a low altitude. It's typically 8,000 feet. The correct temperature, about 70 degrees Fahrenheit or 21 degrees Celsius. If you're flying a turbine-powered airplane, you typically get this pressurized air off of the compressor of the jet engine. That is, you bleed the air off of the compressor of the turbine engine. And if you're flying a piston-powered airplane, you're going to be taking it off of the turbocharger. For instance, a pressurized 210, Cessna P210 has two turbochargers on the engine. One is to pump air into the engine so it can produce horsepower at high altitude, and the other turbocharger is there just to pressurize the engine, or correction, to pressurize the cabin. How does the system operate? Well, first of all, the cabin is nearly sealed. If you take a typical aircraft that's pressurized, and here's our pilot, and up in the nose of the airplane there's typically a radar, so there's a pressure bulkhead up there, pressure bulkhead in the back, and of course we're going to have some doors and windows. The airplane is not completely sealed. The seals are around, the doors are going to leak a little bit, the windows are going to leak a little bit, even the rivets on the skin are going to leak a little bit, and of course if we have flight controls going across the bottom of the airplane, they're going to go through a little hole in the back bulkhead. That's going to leak a little bit of air as well. Now this is normal, this is okay, it's typical, it's expected for some of the air to leak out. Now these are the uncontrolled leaks. And that's all taken into account. You need to understand that we're going to pump air into the airplane cabin all the time, and air is going to leak out all the time. Now those are the uncontrolled leaks. The controlled leaks are typically just one, the outflow valve. For instance, typically in the back of the airplane, there's a valve, the outflow valve. And it moves in and out to change how much air gets to escape. There's three ways to control how much air stays in the cabin. One of them is engine power setting. The higher the engine power, the more air we pump into the cabin, usually near the front. The position of the outflow valve, if it's closer, it's going to let less air out. And also as we climb to higher altitudes, if we climb, let's climb to higher altitude. There we go, now we're at a higher altitude. The difference in pressure between the inside and the outside has a greater difference, so the air is going to leak out faster. Of those three, the only one of those three factors that can change cabin pressure, which are engine power setting, altitude, and outflow valve, The outflow valve is the only one of those three that we're going to use to control the cabin pressure. We don't have to change power setting or altitude just to keep the cabin pressurized. Okay, on the test, I'm going to ask you a question. It's going to go like this. It's going to say, list the three instruments that pilots use to control and monitor the pressurization system. You'll notice that I put the word cabin in italics, and the asterisks are there to remind you, to tell you about this test question. There's obviously the altimeter in the airplane to tell you how high off the ground you are. Then there's the cabin altimeter that tells you the pressure inside of the cabin, or the equivalent altitude inside the cabin. There's also the regular vertical speed or rate of climb gauge for the airplane. Then there's the cabin rate of climb gauge, which tells you how fast the air pressure inside of the airplane is changing, how fast the altitude inside of the airplane is changing. And then there's the cabin differential pressure gauge. The cabin differential pressure gauge tells you the difference between the inside of the airplane and the outside of the airplane, and it tells you this in inches of mercury, or correction, in pounds per square inch. There's a rule of thumb. At sea level, the outside air pressure on a standard day is 29.92 inches of mercury, and that's the same as 14.73 psi. Interestingly enough, if you look at this 29.92 divided by 14.73, that's really, really close to 2. So there's a ratio of 2 between inches of mercury and pounds per square inch. As we go up in altitude, say for instance to 5,000 feet, there's a 5-inch reduction in the outside atmospheric pressure. So let's see, here it'd be 29.92 minus 5 would be 24.92. So at 5,000 feet, it's the outside atmospheric air pressure on a standard day, of course, is 24.92. That's about 25. Half of 25 is 12.5 psi. At 8,000 feet, which happens to be the typical altitude that airplanes are pressurized at, if we use this rule of thumb, it would be 29.92 minus 8, or 21.92 inches of mercury. And half of 21.92, that's about 22. Half of 22 is 11 psi. So typically, we're going to keep the inside of the airplane pressurized to 8,000 feet or 11 psi. If we flew up to an altitude where the outside air pressure was 2 psi, 11 minus 2 equals 9 psi differential. That is, the difference between the inside pressure and the outside pressure is 9 psi. That is the pressure that the pressure differential gauge is going to tell us. Now, every airplane has slightly different controls. We're not going to get into them very much. Essentially, they're either going to be set to go to operate automatic, or if the system doesn't operate correctly, you're going to have to flip a switch and operate it in manual. If it's automatic, there's not a whole lot you do. It controls the cabin rate of climb, so it doesn't change by more than about 500 feet per minute. Most passengers, it gets uncomfortable if the cabin rate of climb is greater than 500 feet per minute descending or 500 feet per minute climbing. So if you have to go to manual, you're going to want to watch the cabin rate of climb gauge and make sure it doesn't exceed 500 feet per minute up or 500 feet per minute going down. For instance, I went to A300 ground school, or part of it anyway, and prior to takeoff, you set in one window the altitude of the airport you're going to fly to, and that was it. The rest of the time is completely automatic. If you have to go to manual, however, what you're essentially going to be doing with the switch is going to be manually opening and closing this outflow valve to take into account the differential pressure and how much air is coming into the cabin. So if you changed engine power settings or you changed altitudes and the differential pressure changed, you'd have to change the outflow position. So as you're climbing up all the time as the co-pilot, if you were in manual, you'd have to readjust where the outflow valve position is. So it's going to take some of your attention. Here is a picture of a Boeing 757, if I recall it correctly. In this system, it's got automatic system number 1, automatic system number 2 in case one fails, and then go to manual. I don't see the switch that would control the outflow on that side of this picture. But you probably can't tell, but this word right here is cabin. Here's the cabin differential pressure gauge. You'll notice that it's got a red line at about 9 PSI differential. So this airplane is probably certified into the high 30,000 feet, somewhere between 35 and 40,000 feet. Here is the cabin altimeter, 2, 4, 6, 8, 10, 15, 20, 25. By 25, I'm not really worried about it, how high it is, because the airplane's depressurized and you have your oxygen mask on. But normally it would be at about 8,000 feet if the airplane was pressurized. And here is your cabin. The rate of climate goes plus 1,000, plus 2,000, minus 1,000, minus 2,000. Here's plus and minus 500. So you would want to take a peek at that, especially if you were doing this in manual, and make sure you didn't exceed plus 5,500 rather, or minus 500 feet per minute, so you wouldn't blow people's eardrums out. Here is the pressurization control panel for an Airbus A300. Again, we have cabin altitude, and it starts telling you above 10,000 feet, we got a yellow arc. And here is cabin vertical speed. Here's plus 5, minus 500 feet per second, or feet per minute rather. And here's cabin differential pressure. You'll notice green arc goes up to about 9. So again, this airplane is probably certified somewhere between, for a maximum certificated altitude, somewhere between 35 and 40,000 feet. You notice here it says manual pressurization. If you lift up this plastic guard and push the button, you'd be going to manual. And here's your vertical speed control up and down. You'd be moving the switch up and down. And here this airplane has a couple of outflow valves. O is for open, C is for close. So you can see as you move this switch, opening and closing the outflow valves, you'll be able to see this open and close. And of course you want to keep a very close eye on the cabin vertical speed. And of course you wouldn't want to let the cabin get above 10,000 feet. Under FAR 121, the requirements for oxygen to be supplied to passengers is if you go above 10,000 feet, boom, you got to give the passengers oxygen. And it also says for FAR 121 as well that the required flight crew, that's the pilots and the flight attendants, they have to use oxygen also above 10,000 feet. Safety features. Yeah, there's a couple of safety features that airplanes typically have that are pressurized. One of them is a safety valve. The safety valve is typically in the back of the airplane, and it's similar to the outflow valve, except that it's closed almost all the time. The safety valve is spring-loaded closed. Let's say, for instance, that this airplane had a cabin differential pressure redline up to 9 psi. So let's say we're flying along and it's 2 psi outside, it's 11 psi inside, so the cabin differential pressure is 9 psi. But for some reason, the automatic system closes the outflow valve a little bit, and more than 11 psi is held into the cabin. The pressure in here is going to be more than 9 psi higher than the outside of the airplane, so this safety valve is going to open up just a little bit. It's like a pressure regulating valve, correction. Let's see, it would be just like a safety valve on our hydraulic system, in that it's spring-loaded and it's only going to open if the pressure on the inside gets too high compared to the pressure on the outside. It'll only open up enough, a little, to let enough air out so that the differential stays just a hair below the red line. That's going to keep this fuselage from getting overstressed. If the pressure on the inside is more than 9 psi than the pressure on the outside, the fuselage, it typically does stretch, but it'll stretch too much, more than it was designed for, and now we'd have to do a special inspection on the airframe. So whether you were in manual or in automatic mode, and the airframe was accidentally going to be overpressurized, that is, the differential pressure would go above red line, hopefully the safety valve will work and not allow that to occur. There's also typically a squat switch on airplanes that are pressurized, so that when you land, when you touch down and the main landing gear compress, because the weight of the airplane is on the landing gear, it closes the switch and the outflow valve slowly opens. The outflow valve slowly opens. So that way, by the time, and it's not all at once, it's nice and slow. So when you land the airplane or taxi the airplane and go to open the door, if it's the big airliner type that opens inward, the door has to be able to open by having the pressure on the inside and the outside be the same, so you can open the door. On big business jets, big business jets, and such small business jets for that matter, typically the door has the stairs in it,
and the door is going to be allowed to go open, and then of course it's got some cables on it. So you, the co-pilot, are going to come up and let it go down easily, or somebody on the ground is going to come up and put their arms up so the door doesn't go kaboom when it goes all the way down. If, for some reason, the outflow valve stayed shut and the pressure inside of that airplane was 0.5 psi higher than that on the outside, and let's say that this door was 30 inches by 60 inches. 30 times 60 is 1,800 square inches. Force equals area times pressure. In this case, 1,800 times 0.5 psi. If it's 0.5 psi on the inside greater than the outside, we have 900 pounds of force pushing this door out. So it would whack this person on the ground, whack their head, or it would pull you out because you're holding on to it. So you go whee as the door flung open really, really fast. So having the squat switch to slowly ensure, no matter what the system was doing, whether it was manual or automatic, to make sure that the airplane is completely depressurized by the time you open the door, that's a positive thing. Okay, cabin airflow. The outflow valves are typically in the rear, certainly on small airplanes they do that. The air typically enters the cabin at the front of the airplane where the pilots are and leaves at the aft part of the airplane. I think when you do the 777 homework, you'll find that it has an outflow valve in the tail and an outflow valve in the middle of the fuselage. Typically, the average air molecule at cruise, once it enters the cabin, the average air molecule leaves about 3 minutes later. Obviously, the slower the air goes, the greater buildup of carbon dioxide and the lower oxygen content. So keeping the airflow doing it about 3 minutes, that's an FAA requirement. However, interestingly enough, in the last 15, 20 years, to save fuel, airliners have been built with recirculation systems. You need to understand that pumping air into the cabin, taking bleed air off the engines, it takes fuel to compress that air. So if we turned off the air conditioning pressurization system, we burn less fuel. Well, of course, we'd have to use oxygen and such. But if we had a recirculation system, so that some of the air at the back of the airplane would be ducted back to the front of the airplane and travel through the airplane again, it's already the right temperature, it's already the right pressure. Now granted, with this recirculation system, there is going to be slightly higher levels of carbon dioxide, slightly lower levels of oxygen, but the FAA and the airlines don't feel it's bad enough to harm anybody. Interestingly enough, of course, this recirculated air never gets recirculated up to the cockpit. The recirculated air comes back into the cabin aft of the flight deck. So the pilots never get any of this recirculated air. Not because they're worried about your carbon dioxide and oxygen levels, but if there's smoke or fire in the cabin, it wouldn't pump this smoke back into the cockpit. Of course, if there was any smoke or fire, you'd put on your oxygen masks and your goggles and not have to worry about it anyway. Also, if there's a fire or smoke, you can, as a pilot, turn off the recirculation system. So it is manual set up so you can manually turn off the recirculation system. But typically you're going to run the recirculation system as a standard operating procedure because that's what your airline would like you to do. Now, HEPA filter on a lot of these airplanes, the recirculated air goes through a filter, so it gets rid of most of the germs, but all the airplanes don't have these filters, and how well they work would be a rather interesting extra credit assignment. If you're sitting in the passenger seat of an airplane and you look up on the overhead panel, there's those little vents so it'll blow on your face. That's typically the coldest air that goes into the airplane. It's also there to keep you from getting nauseous. Airlines certainly don't want their passengers getting nauseous and throwing up because it'll make everybody else do the same thing. And so they usually keep, they keep the air conditioning system running during takeoff. I had a flight engineer student who flew on C-141s, and they turned off the air conditioning system for takeoff to get a little more thrust. But if you were in a civilian airline and they turned off the air conditioning system for takeoff and lots of people threw up, then they probably wouldn't fly on that airline anymore. So typically, or I've always heard that on all civilian airplanes, they always leave the air conditioning pressurization system on for takeoff, even though it does reduce their power just a little tiny bit, but that's taken into account. That's normal. Here's a picture of a gasper. You can see the little vent, a little overhead. Okay, you're flying along in an airplane that's pressurized. You're at high altitude. Guess what happens at high altitude? The temperature is really, really cold. Even if the relative humidity is high, like you're flying through a cloud, if you heat that air up from, say, minus 56 Celsius to plus 21 degrees Celsius, and there's the same amount of moisture in it, the relative humidity is going to go way, way down. And we'll talk about it here shortly, but there's also a water separator in the air conditioning system, so it gets rid of any excess water anyway. So the air coming into the cabin is extremely dry, say less than 1% relative humidity. If you've ever sat in a cabin, a pressurized airplane, and you pull out a piece of bread in 5 minutes, boom, it's dried out because the air is so dry. There are two negative effects on the human body because of this dehydration. One of them is fatigue, F-A-T-I-G-U-E. You get really, really tired. The other negative effect is that it tends to cause headaches. It tends to give you a headache. So you're flying along after 5 hours, you're one of the pilots, and finally the dehydration negative effects kick in just before you start descending, and you're tired and you have a headache, but now you have to go and land the airplane, fly the approach, talk to your traffic control, run the checklists. So this is one of the worst times to be tired and have a headache. So to prevent that, you need to drink water. Drink water. You need to remember that if you're thirsty, you're already dehydrated. So I recommend that when you start flying professionally, or even when you're in a passenger of a pressurized airplane, drink more water. I'm not saying don't drink caffeinated drinks. Yes, it's true they're a diuretic, they make you go pee, but drink water in addition to that so you don't have a headache and you don't get tired. Of course, any drugs you take over the counter or prescription, their effects are typically magnified because of less oxygen, so you want to take that into account as well. If you have a decompression, the airplane depressurizes. Obviously, you're going to follow the checklist or the standard operating procedure of the organization you're working for, but here's the generic list that you're going to need to know for the test, and you're going to need to know these steps in order. The very first thing you're going to do is put on your oxygen mask. But just because you put on your oxygen mask doesn't mean that you're getting oxygen. We're going to cover oxygen systems in another section, but you could put on the mask and inhale and get gases coming into the mask, and you go, oh yeah, great, cool, I'm getting oxygen. But in reality, you might just be getting cabin air, and if you're at 36,000 feet, it's only pressurized to 36,000 feet if the airplane's depressurized. So you pass out in 30 seconds, or at least only have 30 seconds of useful consciousness. So the second step after you get your mask on is to confirm on their oxygen regulator that the oxygen is actually flowing to your mask. Make sure the oxygen is actually getting to your mask. Once you're good and you're not going to have pass out or become unuseful, become useless, then you're going to notify the other crew members, the other pilots, the flight attendants, and once you've gotten them notified so they can get their oxygen mask on and check that their oxygen is flowing, then you can worry about the passengers. In transport category airplanes, there's typically an arming system, so if the cabin goes above 10,000 feet, the masks will come out automatically, but I recommend that you confirm that the masks have moved or have come down, and if they haven't, there's a manually operated switch that you can flip so the masks go down. Once you've made sure that the passengers are going to be okay, they're going to get oxygen, then you're going to need to start a descent. Now, some people would say, oh, Mr. Johnson, let's try to fix the depressurization problem first. We might be able to fix it in a few minutes, and then we wouldn't have to descend it. Well, that's an accurate statement. If you could fix it in a couple of minutes, you wouldn't have to descend. But you need to understand in transport category jets, the passenger oxygen system is only a little bit more than what it takes to do an emergency descent. They'll figure out how long it takes for that airplane at its maximum certificated ceiling, or maximum certificated altitude, say 39,000 feet. How long is it going to take to get down to 10,000 feet? If you pull the throttles to idle, pop out the spoilers on the wings, nose the thing down at the red line indicated airspeed, how many minutes will it take to get to the ground? Well, let's say it takes 10 minutes. You're only going to have a little more than 10 minutes, not to get to the ground, but to get to 10,000 feet. The passengers only have to be supplied oxygen until you get to 10,000 feet. Now, you don't want to have a whole bunch of emergency oxygen equipment in the airplane because it'll weigh too much. So you only have enough oxygen for the passengers to get oxygen during that descent. If you stay at altitude for 3, 4, 5 minutes trying to fix the problem and you still can't fix it, and then you start to descend, halfway down, the passengers are going to run out of oxygen, they're going to start passing out, and if some of them have health problems, they might even die because of it. So don't wait to start your emergency descent. Of course, as soon as you start leaving your descent, somebody's going to be flying the airplane. The other pilot needs to tell air traffic control what you're doing so they can get people out of your way. So on the test, you need to be able to come up to list as a fill-in question these checklist items, what to do in case the airplane depressurizes, and write them in order. If you have any questions about pressurization systems, send me an email or ask me in class. Next section is cabin heating and cooling. On small airplanes like 172s and Seminoles, that needs to be covered in your ground school. So this slide right here, you can cross it out completely. Do not answer the questions in the practice questions. I'm not going to give you a homework evaluation out of the yellow pages on this slide, and there are not going to be any. That is, there will be 0 questions from this slide on the test, so you can cross this slide out completely, take ground school, and you can learn about it there. Okay, small reciprocating air engine aircraft air conditioning. Reciprocating is the same as it's piston powered. This system is identical to the one that's found on the car. Here you can draw it. It's called a vapor cycle machine. You'll notice on a vapor cycle machine we've got a compressor, we've got a condenser, we've got an expansion valve, an evaporator, and those are the main components. So you may have to hit pause so you can draw this. We've got the compressor, and then the squiggly lines is the condenser. Here's the expansion valve. Here's the evaporator. Now inside of the vapor cycle machine is a refrigerant. It's Freon. We'll get into that here shortly. Freon changes its state of matter based on pressure and temperature reasonably easily, but it takes energy to change its state of matter. For instance, the compressor, it's driven off of the engine usually. On a little airplane or your car, it's driven off of a fan belt, and it pulls in. I've got a couple of arrows here that's showing the direction that the Freon is traveling. We're going to pull in low pressure vapor. It's warm, so we're going to pull in low pressure vaporous refrigerant. The compressor is going to increase the pressure, so now we have high pressure vapor. This high pressure vapor, since we compressed it, it's hot. So we're going to run it through a heat exchanger. That is, we're going to blow outside air across essentially what looks like a radiator, and on your car in front of your radiator is what looks like a small radiator. That's the air conditioning condenser. We're going to blow outside air across it, and the air is going to get hotter. It's going to take energy away from the Freon that's traveling through the condenser. And if we take enough energy away from it, it'll turn from a vapor into a liquid. It'll go from a high state of matter to a lower state of matter, just like if we take heat out of water, it'll go from a liquid to a solid. So in this case, it's going to go from a vapor to a liquid, just like steam, just like water vapor turning into water if you take enough heat out of it. So as the Freon or refrigerant goes through the condenser, the outside air blows across it, heat comes out of the Freon, heat goes into this outside air. We blow the outside air overboard. We don't want it. Now we have liquid and high pressure Freon. As this liquid high pressure Freon gets to the expansion valve, here's a picture of the expansion valve. The Freon goes through it, and there's just a little tiny hole. In fact, we could call this a metered orifice. As the high pressure liquid goes across or through this little hole on the downstream side of the hole, which is right here, it's getting sucked in by the compressor. So the pressure on the downstream side is low pressure. So it's high pressure liquid. On this side, it's low pressure on the opposite side. The liquid tends to expand since it's low pressure. Now, under low pressure, as the liquid tries to expand, it wants to turn into a vapor. However, to go from a liquid to a vapor, it needs energy. So we're going to blow outside air again across this, what looks kind of like a radiator. In this case, it's called an evaporator. We blow outside air across the evaporator, and this air gives up heat energy and gives it to the Freon. So the Freon has heat energy, so it can go from a liquid to a vapor. It goes up from its state of matter of being liquid to a vapor. So it warms up, but the air going through it has heat taken out of it. So this cold air is now sent to the cabin. In your car, if you notice on most cars with air conditioning, you can hit recirculate. Recirculate just means that it pulls in cabin air and runs it through the evaporator. If it's already cold, it gets colder. Even still, we can get the greatest cool air into the cabin if we run it on recirculation. Now, this freon going to the evaporator goes from a liquid to a vapor. It pulls in heat energy, so the air going across it gets colder, but it goes from a liquid to a vapor, so now it's low pressure and a vapor, and the cycle starts all over again. This is the diagram for a vapor cycle machine. Now, to get this air to go across the condenser, typically, somewhere in the airplane, there's a door that's open to let outside air across it, and of course, this creates drag. And of course, the compressor is bolted or connected to the engine rather, and it takes horsepower off of the engine. So, vapor cycle machine, people typically call it the air conditioner on their car. You do not have to memorize Freon R12 or R134A. The Freon R12 is the bad Freon that goes up to the ozone and destroys the ozone, and the Freon R135 does not do that. It doesn't destroy the ozone. Let's see. Typically, on small airplanes and on your car, the compressor is driven by a fan belt off of the engine. But I'll show you before this version is over, before this lecture is over, that you can drive the compressor of a vapor cycle machine. You can drive it with an electric motor. And of course, I cover the condenser, the expansion valve, the evaporator, and of course, if it takes, say for instance, 2 or 3 horsepower to spin the compressor, it takes it off of the engine. So for takeoff, you're always going to see in the checklist that you turn off the air conditioner. First of all, you're going to want to get the engine power, and second, not being taken off by the compressor, and you want this door to close so you don't have the drag for takeoff. And you're going to do it for landing. The approach checklist is also going to say turn the air conditioner off. Again, in case you have to go around, you won't have the drag from that door, and you'll have all the horsepower available going to the propeller. And of course, if you turn this on during cruise or climb and you maintain the same airspeed, you're going to have to push the throttle forward a little bit to keep that same airspeed, since it's going to take power off of the engine. Now, if you start flying turbine-powered aircraft, transport category jets, big biz jets, big turboprops, the air conditioning system is going to be what's called an air cycle machine. An air cycle machine. Air cycle machines on these big jets are also called the air conditioning pack, or air conditioning packs, because there's usually more of them. There you can see the air cycle machine. The air cycle machine, what you might want to do is hit pause and draw this and then hit it again while I'm explaining it. The bleed air comes from the compressor of the engine, and it goes through a heat exchanger. We're going to blow outside air across it and get rid of that outside air. That cools the bleed air down because it's already hot because it got compressed by the jet engine. Then it's going to go through a compressor to increase the pressure quite a bit, and I'll get through this stuff in a second. The expansion valve looks similar to what the expansion valve in a vapor cycle machine, except that we're going to be gas on both sides, or vapor on both sides. What we need is a really, really high pressure on the upstream side, so then when it goes through the hole and it's low pressure, it'll expand quite a bit and it'll cool quite a bit. So just the pressure coming out of the engine isn't enough, so we need to compress it to a higher pressure even more. Unfortunately, compressing it causes it to heat up, so we're going to run it through another heat exchanger. Again, we're going to blow outside air across it. On the ground, we'll have to have a fan blowing so this outside air across these heat exchangers. In flight, we can just use ram air and you don't need to run the fans. So it cools the air down a little tiny bit, and then we blow it through the turbine. The air comes through the turbine. It has a velocity. The turbine is just there to extract energy to spin the compressor. This whole system here does not take electricity. It doesn't have an electric motor. It doesn't have a hydraulic motor. It gets all of its energy from the velocity and the pressure of this air coming off the engine. So we're going to extract some of that with the turbine to drive the compressor. Now, so the air coming up to the expansion valve is at a very high pressure. Here's the expansion valve. As the air goes through that orifice, it's going to expand rapidly, and the temperature is going to go way, way down. So we're going to have high pressure air, and it's going to get colder leaving the expansion valve. The expansion valve is where the vast majority of cooling takes place in the air cycle machine. Now right after that, we're going to have a water separator. Downstream in these ducts going to the aircraft, to the airframe, if there's water vapor, the water might freeze and a valve might get stuck. So there's going to be a water separator to get the water out. So here's, even if the water the airplane's flying through has a lot of water in it, we're going to get it out. And so we're going to have rare, very, very dry air going to the cabin. Right after the water separator is going to be the mixing valve. The mixing valve decides how much more bleed air. There's actually another line coming from the engine, more bleed air, but that's hot. And it's going to mix with the cold air coming out of the expansion valve and the water separator. And this mixture of hot and cold air is going to go to the cabin. When you set the temperature in the cabin, that's going to change the ratio of cold air to hot air. Every time you turn that knob, colder or hotter, it's going to change the ratio of the cold air to the hot air. And so that's what that mixing valve does. That's an air cycle machine, and you typically find air cycle machines on transport category jets, big biz jets, big turboprops, and big old honking helicopters, turbine-powered helicopters. Air cycle machines are sometimes called ECU, Environmental Control Unit. Environmental Control Unit. And I covered the heat exchangers, the compressor, the turbine, the expansion valve, the water separator, the mixing valve. Of course, this air right here, this is the air that goes to the front of the cabin to pressurize the airplane. That air right there is what gets pumped into the front of the cabin. So it's going to take power off of the engine. Of course, this is better than having people pass out because you didn't train them very well, and we got to heat the cabin anyway. But it's going to take fuel. It's going to burn a little more fuel than it would otherwise, but this is normal. This is the typical way you plan your flight. And fuel burn is to run the air conditioning / pressurization system. Now, small business jets and small turboprops, such as the Beech 1900 that flies in and out of the airport, typically have a slightly different air conditioning pressurization system. This diagram you have in your topic outline. Now, a Beech 1900 is just a big old honking King Air. King Air's Beech 1900s have two turbine engines. They're turboprops, but they're turbine engines, so they have compressors. And to pressurize the airplane, to keep it at a high pressure inside the cabin, bleed air is going to be taken off of the compressors and routed to the front of the airplane. Now, this is good for small business jets and small turboprops. But this airplane is small enough that it does not have an APU. That vapor cycle machine on the air cycle machine on the ground, this bleed air can come from an APU on board the airplane. So we can be out in the middle of nowhere at an airport with no surfaces and fire up the APU, and we can route this bleed air, part of the pneumatic system, into the air cycle machine, and we can run the air conditioning on the ground. But if we're in a small turboprop or a small business jet that does not have an APU, then we won't be able to run the air conditioner if we had an air cycle machine. So on small business jets and small turboprops, they're commonly going to have a vapor cycle machine. Up here in front of the airplane is going to be the compressor, condenser, evaporator, and so on. Except now this compressor, instead of being run off of a fan belt directly off of the engine, this compressor is going to be run by an electric motor. So on the ground, if all we want to do is cool the airframe, we can turn on the master switch and have the battery power the electric motor that spins the compressor, and we can blow cold air into the cabin. The downside, the disadvantage of this system is that if you run it for more than 15 or 20 minutes, you're going to drain the battery so much that you cannot start the engines. So the disadvantage here is that you really need a ground power electrical cart, some source of electrical power on the ground to run this if you want to run it for an extended period of time. The advantage is that if this were an air cycle machine, we'd have to start up one of the engines
to get bleed air off of it to run the air cycle machine. And of course, if you had the propeller spinning around, you tend to chop up ground personnel and mechanics and stuff like that. So the advantage is that you can have an air conditioning system that will run on the ground, but you don't have to run an engine. So the advantage is you don't have to run the engine on when you're on the ground to cool the cabin. The disadvantage is that if you want to run it for an extended period of time, you really need electrical power from the ground. And which aircraft have the system? Small business jets and small turboprops. If you have any questions about cabin heating and cooling, don't hesitate to send me an email, or if you marked the questions, you can also ask me in class.